changes as element and isotopic changes. For example, masses 107 and 109 different isotope change. This is irradiation zone. This is after screen, on the screen. Excuse me. We can observe hot points on the sample as beta emission from irradiation palladium or titanium or other materials. This may be results for structure damage as electric field change for after changes surface and for example we can observe different
That's okay. So, next speaker is Dr. Zhang. Oh, no poster. Okay. Dr. Passer.
The poster by Zhang, I believe, will be posted, but there is not going to be an oral presentation.
Thank you, Mr. Chairman. I'm reporting some work on other people's samples. Now that I'm retired, I do it on my own money. And so I can't afford too many things, but I was fortunate to have some samples loaned to me from Professor Arata's work at Osaka University. And I have 4 of his samples of a powder palladium in the center hollow part of the cylinder of his cathodes. And I decided to subject them to neutron activation analysis. And the one thing to look for is this one column here. This one here. It shows the amount of zinc 64. I observed in 4 samples. The virgin sample, unused, is D. And these are the active ones which produce something like 30 or 40 megajoules. And these are parts per million by weight. The only thing I measure is zinc 64, and I'm inferring these numbers would be true if we had natural zinc. But if we have just zinc 64, the parts per million by weight would be these in parenthesis. And I assume the virgin is natural zinc. In any case, we have factors of 8, 14, and 7, roughly, increases as a result of them being exposed to fairly high-pressure deuterium in the center of those cathodes for the order of months. In addition, I decided to also see in the same samples if there was any indication of changes in the palladium isotopic ratio, taking the ones that I could access, which are palladium 110 and 102, and the ratio of 110 to 102, as you can see, for the virgin I assumed 1, and relative to the virgin, 20% increase in the C sample, a 6% increase in the B, and 24%. Just outside the limits of error, an increase in, or decrease in 102 relative to 110 may indicate that the lighter isotopes, if we're having fission here, and that's a very big step to suggest, are the more vulnerable to fission. Then I also observed iridium 191 and gold in these samples, and in every case except one, we had increases in iridium and increases in gold. We had a decrease in the iridium in sample B relative to the virgin material. But in every case, we had an increase in the gold content, a factor of 1.7, 1.1, and 5.3 for those active samples. How could this happen? Well, I assume that it might be possibly for zinc fission of palladium, and these are a couple of reactions, but it also is possible that copper-63 impurity could be proton capturing. Thank you.
Our next presentation is by Dr. Monti.
Okay. I report some results I already presented in the ICCF-8 in Vancouver, in which it was possible to show the reality of seasonal effects in low-energy nuclear reactions. To make a further demonstration of the reality of these experimental results, a third series of tests was carried out on May 21 and May 25, 1998. The first experiment, May 21, showed a fermentation of 1.32 grams, 30% of the total of uranium. The uncertainty declared by the laboratory was between 5 and 10%. To avoid any possibility of error, we decided to show the possibility to increase this result through a slight change in the proprietary formula used, suggested by the alpha-state model of the atom. Consequently, a second test was carried out on May 25, 1998, with the only addition of 50 grams of SiO2 powder in the same composition used for the first test of May 21. The results were a fermentation of 2.7 grams of uranium, 45% of the total, an increase of 50% compared to the test of May 21. I can give more explanation of this, but under request of Francesco Scaramuzzi, we decided to show all the experimental details of a similar test. The repetition of the test made by Professor Box at ISCMNS in 1992, showing the errors of this experimental procedure due to the lack of knowledge of elementary alchemy, which caused the lack of repeatability in his test of metal production. This will be shown in the box.
Our next presentation by Dr. Wysocki.
I'd like to present the result of our experimental investigation of the problem of controlling nuclear decay. It's a very interesting problem, of course. In the case of space, this problem is solved easy, and the corresponding probability of gamma decay is fully determined by the nuclear characteristics. But in the case of the problem becomes very complicated when material bodies exist in the surrounding space. We have considered the general system that included the excited nuclear, the quantized electromagnetic field, and atom electrons, and also the controlling and controlling screen. The controlling nuclear decay, it is a result of interaction between the nucleus and electromagnetic field in their energy states, and also the interaction between the electromagnetic field and controlling screen. We have obtained the general solution of this system and also several solutions for main case. For example, for the case of Nussbauer screen, we have the following expression for total and radiative controlling time of light. In this expression, there is a parameter, this parameter of Nussbauer probability. It is a solid angle that screened by our screen, and also it is a radiative shift. It is a nuclear analogy of the famous lamp shift. On this figure you can see the installation or the scheme of national experiment. The controlling screen was fixed in the center of resonance screen made of stable iron-57 isotopes. Behind the two diaphragms there were two amplitude detectors for measuring of 2 quants of cascade. For cascade with energy about 122 keV and 14.4 keV. After this, the result of measurement, after 2 signals from the detectors were used for measuring of law of gamma decay in the processing system. The measurement of this delay of the second quantum, of the gamma cascade was performed in 2 regimes. In first regime, we used only resonance screen. In second regime, the round cylinder made of lead was put on this result. In result of experiment, we have discovered the change increase in the mesbauer radiative lifetime by 10 or more %. Thank you.
Our last speaker is Dr. Robodanov.
I tell about a new effect which we discovered. Time very low, and I begin with end. If you plate of hydrate forming material, for example, palladium, vanadium, niobium, etc. One side, on one side, we cover thin films. Thin films with molecular permeability. This sample with coating cover, it's need heated up to definite temperature. Then through this sample, it's need passed hydrogen. You have effect in both quantity. If you hydrogen passed through sample with cover on exit side, you may have excess heat generation. If you hydrogen passed on cover on enter side, the second you have loss heated. You have heat absorbed. Effect unlimited on time. In our experiment, we have power about 1.5 watt. Specific power about 0.4 to 40 electron volt on atom passed from this system. Thank you.
So I think we've done very good. We have 15 minutes ahead of time, so Mike and I decided if we do the singing, I will do the dancing. Sure. You ready to sing? So I think we can go now to the poster session that lasts up to 7 p.m. I think. Okay. Thank you very much for your attention.
before our section, I want to give small information about Russian conference. It will take place, as usual, in Sochi, in Russia, this year in October. The list with this information lies in the registration table, and you may take it. Understand? Is some questions?
So now we can start this lecture section. First speaker is Dr. Michael Mikuza. 50 minutes speaking and 5 minutes for discussion.
Good morning, ladies and gentlemen.
May not be on.
Is this microphone on?
No.
One, yeah.
What I'm going to talk about this morning is what I somewhat grandly describe as an emergence of a coherent explanation for anomalies observed in the deuterium, palladium, and hydrogen-palladium systems. Specifically, this morning I'm going to talk about evidence for helium-4, helium-3, and tritium production. Obviously, this is a big topic. There are many things that might be covered under this title. In order to restrict myself, I'll talk simply about these three light element anomalies. The work has been performed largely at SRI International by myself, Fran Tanzella, and Paolo Tripodi, who are present in the audience. But I do need to acknowledge a long list of collaborators in various aspects of the work that I'm going to talk about, particularly Professors Arata and Zhang, Ben Bush, Steve Crouch-Baker, the two Brians, Brian Clark and Brian Oliver, who were involved in helium-3 analyses, Russ George, Vittorio Violante, who is my chairman this morning. This was the abstract that I submitted to the conference. I think everybody in the audience is aware that numerous observations have been made of what we call apparent anomalies in quite carefully performed experiments in the deuterium, palladium, and hydrogen palladium system. And there's quite a diversity of observed anomalies. Prompt emission of electrons, charged particles, unexplained excess heat, which is the work that we've done for so many years ourselves. Residual presence of light element anomalies, helium-4, helium-3, and tritium, which I'll talk about specifically today. Others here will talk about heavier element isotopic anomalies. There are also some unusual, very unusual conductance properties in highly loaded deuterium, palladium, and hydrogen palladium systems, which I won't talk about. Basically, the theme of my talk, which is not going to be well developed, but the theme of it is that all of these anomalies can be accounted for, and can only be accounted for, if we consider that the lattice forms an extended coherent system. This is a particularly appropriate observation in view of the commemoration of Giuliano Preparata's unfortunate death. So what I'm going to describe is a series of experiments which really show up the presence of these light element anomalies. The first one I'm going to talk about was performed a long, long time ago. Many of you will have heard this before. This experiment was performed by Ben Bush, perhaps as many as 8 years ago, in a rigorously metal-sealed apparatus, open cell calorimetric operation with a liquid nitrogen blanket to exclude helium-4. And the object of this experiment was really to reproduce the work performed by Mel Miles and Ben Bush, in which the first evidence was developed for a correlation, a quantitative correlation between the appearance of helium-4 and excess heat production. we were seeking to reproduce this experiment in a somewhat better designed system, an all-metal system, integral boundary calorimeter, much more sophisticated exclusion of possible helium-4 ingress. The results that we obtained at that time were suggestive and certainly confirmatory of Mel Miles' observations. If you look at this slide, what we observed is that in all cases, these points show measured helium in parts per billion, I'll note on this axis, correlated with the excess power that was observed in the calorimeter. In 3 occasions we observed excess power and we observed quantitatively correlated helium-4. This line is the expectation line. This line is what you would expect in terms of helium-4 yield if the reaction that you're looking for is D plus D to helium-4 plus 23.8 MeV of lattice energy. As you can see, the line that we see falls a little bit below, so that there is some possibility that we are missing some component of the helium. And the only real difficulty that we had with this experiment was that in 3 occasions when we observed excess heat along this axis, there was no observable helium was measured. So we took this experiment to be suggestive and confirmatory, but obviously we needed to do a better job. So the conclusions of those, which were reported in this final report to the Electric Power Research Institute here, results support those of Miles et al. In a more closely sealed apparatus, were consistent with D plus D going to 24 MeV of energy in the lattice. Helium was observed only when excess power was present. The concerns that we had at that time, the small absolute values of the excess power and helium, because the cell had a very small working volume, and the background level, of course, for helium is so high. Background level of helium in the laboratory that we work in is 5.22 parts per million, and the amounts of helium that we were observing in these open cell experiments were in the parts per billion range. The other concern was the missing helium or helium hideout in experiments where excess power was observed. On 3 occasions we didn't observe the helium-4 that we expected to be present. The question is why? The more recent experiments performed closely in conjunction with Les Case and Russ George, at least initially, we developed some closed and sealed metal vessels into which we inserted a palladium on carbon catalyst, 0.4% and 0.5% palladium on carbon catalysts, immunized catalysts. We pressurized these vessels with either deuterium or hydrogen in the range of 1 to 5 atmospheres. These cells were operated at temperatures between 175 and 250 degrees C in a non-isothermal mode. We had our usual online real-time data acquisition, online monitoring for helium-4, and some sort of correlated heat flow calorimetry. So the experiment looked something like this. We have 2 vessels. These are 500 cc stainless steel vessels with conflat sealed, conflat seals, I guess. Through the top of the vessel penetrates one gas line for admission of hydrogen in one case, deuterium in the other case in these paired experiments. We have a thermowell into which we can insert a series of thermocouples to measure the temperature gradient in the axial direction. This gas line now terminates at a sample manifold. The gas manifold looks somewhat as shown here. We can take our samples for admission through a liquid nitrogen cooled carbon trap, admission to the mass spectrometer, and we have various lines available for sampling of standards, helium-4 in deuterium samples, air samples to compare the measured helium-4 levels with the ambient background, and so forth. The mass spectrometer itself is capable of baseline resolution for the 2 mass 4 peaks, so I don't need to explain this in detail. But we have the 2 mass 4 peaks, the lower mass peak obviously being helium-4, the higher mass peak being D2, and it's a simple matter in this experiment to resolve the 2 mass 4 peaks so we can't be confused by deuterium in the measured helium-4 signal. As a matter of practice, what we normally do is operate the liquid nitrogen cooled carbon trap in such a way that no D2 is admitted to the mass spectrometer at the time that helium-4 is being measured, but it is possible to warm up, or at the end of a long day's experimentation, there's some leak through of D2 so that we can see the 2 mass 4 peaks and be comfortable that the peak that we're observing is helium and not deuterium. We performed in the last year or so something like 16 experiments in this mode, and they fall into 3 basic categories of performance. Let's say a third of them do nothing at all after admitting deuterium to these palladium on carbon catalyst samples for long periods of time, days, weeks, months. The signature of helium-4 does not increase with time, nothing happens. The experiment is relatively uninteresting, we soon lose interest in it. Second category of experiments, you see something like an exponential increase in the helium-4 signal, generally terminating below this ambient background line. So the dotted line that I have here is 5.22 parts per million laboratory background. These experiments are significant. They show a significant increasing of the helium-4 signal in a rigorously metal-sealed helium leak type cell. The experiments that are somewhat more interesting, or it's certainly more immediately interesting, are the experiments in which, for a period of time ranging between 5 days and 15 days, there is no apparent increase in the helium-4 signature. Then the helium-4 signature will increase quite rapidly, somewhat following a vector as such. And in some cases, 1, 2, 3, 4 cases shown on this slide, the helium-4 signature rises to exceed the laboratory ambient background, giving us confidence that the helium that we see in this experiment is not derived from leakage from the ambient. If we take one of these signals and see if we can find some correlation with heat, obviously this rate of helium-4 increase is quite sharp. The derivative d helium-4 dt is sufficiently sharp that we might expect to see the commensurate heat. So that we can look at our calorimeter. I use the word calorimeter in inverted commas here. If you remember the experiment, this was not designed as a calorimeter. These experiments were designed to produce a helium-4 signature and measure it, but we did instrument with a series of thermocouples, so that we have thermocouples in the carbon catalyst bed at the bottom of the cell, thermocouples in the gas phase halfway up the cell. We also have thermocouples on the lid. This is a stainless steel dewar. I should describe the heating arrangement. There's an electrically powered heater helically wound around the bottom of this surface. This yellow material here is a solid insulation. The whole is packed inside a stainless steel dewar. So the object is to heat the catalyst and allow heat to leave this system in the axial direction. So there's a gradient of temperature from the bottom of the cell in the catalyst bed to the top. By measuring the temperature at this point, the temperature at this point, the temperature in the ambient, and also the temperatures at the top here, we can look at the gradient of temperature in the normal direction and compare the two. So we can have what I call a differential calorimeter, compare the gradient of temperature between the active cell, in this case vessel 2, the blank cell, in this case containing hydrogen, vessel 1, see if the temperature difference between the bed and the air in the active cell is different from the temperature difference between the bed and the air in the blank differential mode calorimetry. You can also look at the gradient of temperature in the two cells. So I have two ways of calculating the heat leaving this experiment. We do that exercise for one of the helium-4 signatures that I showed you in the slide preceding this last one. Here we have reference to the left axis, the helium-4 signature, the red point, so the helium basically baseline, the initial value in this cell was something like 0.34 parts per million helium-4, which is the amount of helium-4 present in the deuterium charging gas. There's no increase. There's a relatively modest increase in helium-4 signature with time, and then a much more rapid increase of helium-4 signature with time. So the red line is the observed helium-4 signature. You can see here I've subtracted the 0.34 parts per million, which is the baseline, and we have a gray curve. So nothing, slow rate of increase, rapid rate of increase. And then the two curves here, the blue curve and the green curve, are the differential mode calorimeter and the gradient mode calorimeter. Two separate attempts to measure the amount of heat leaving this experiment. As you can see, both the differential and gradient mode calorimeters appear to correlate quite closely with the form of the helium-4 signature. So the blue curve and the green curve represent an integrated excess power calculated in these two modes of calorimetry, so that we can compare the integrated power, the energy, with the amount of observed helium-4. And there's quite clearly a good temporal correlation between these two signatures. If we take these two modes of calorimetry and now compare, let's try and find a Q value for the reaction, which apparently couples heat with helium signature. We have the following picture. So now we have the helium increase on the horizontal axis, the estimated energy in kilojoules on the vertical axis, certain uncertainties assigned to the two modes of calorimetry and also to the measurement of helium. As you can see, there's a good linear correlation between the observed energy and the observed helium-4 integrated in the vessels. Now the slope of this line is not quite what I would have hoped it to be. The slope for this line, obviously, we're predicting a slope of 23.8 MeV. The observed slopes are 31 plus or minus 13 and 32 plus or minus 13 MeV, so the expectation value lies within the analytical uncertainties for the experiment. But I submit to you that the reason that the slope is not 24 is not because of an analytical error in the experiment. It's because not all of the helium-4 presents itself immediately to the gas phase to be made available for to the mass spectrometer for analysis. No, water. Sorry, I'm drying out here. So the conclusions from this particular experiment: a strong time correlation between heat and helium production. The rates were quantitatively consistent with D plus D going to helium-4 plus 24 MeV of energy in the lattice. The concerns in this case were the partial heat flow calorimetry. This is not calorimetry in the sense that we have developed in the past. This is not a rigorous mass flow calorimeter. The calorimetry could certainly be improved somewhat. And the issue of missing helium or helium hideout, not all of the helium that we expect to observe is presented in the gas phase for analysis. This last point can be cleared up somewhat by examining the results of an experiment that we performed previously, and it also provides some illumination into the mechanism and the appearance of helium-4. We'd operated previously an experiment more closely akin to Fleischmann-Pons solid palladium cathodes, aqueous electrolytes, rigorously metal-sealed apparatus, closed cell operation, pressurized cell, online data acquisition. We also had integrating neutron and X-ray monitors, which are not relevant here, mass flow calorimetry, and then submitting samples for helium analysis ex situ. This result, which contains more detail than we need to discuss at the moment, and I in fact presented this at ICCF-8 in Monte Carlo. We don't need to investigate the detail. The blue points are the observed excess power for a particular period of time in this experiment, covering 460 to 700 hours. The green line, in fact, is the prediction curve that I had for my in order to correlate the appearance of excess power with the three variables that we believe to be important: the excess loading, the excess current density, and the rate of change of the loading, that is the gradient, the flux of deuterium through the interface. But just concentrating on the blue points, we observed some excess power. So remember those two blue bumps. If we integrate the power observed during that period of time and calculate an expectation value for the helium-4 in that particular metal vessel, we follow the blue curve in this slide. So the initial value of helium-4 in the deuterium also is 0.34 parts per million. That's our baseline value of helium-4 in the deuterium that we were using. If we integrate the excess power to an expectation value for the helium-4 to be observed in that metal vessel, we get something like 2.5 ppm. What we in fact observed was this point here, which is only 62% of the expectation value. So at the end of this period of excess power production, we had observed an increase, a clear increase in the helium-4 signature, but we hadn't got quite as much helium-4 as we had expected, consistent entirely with the results from the two previously described experiments. So we took a sample of this, at this point, quite a large sample, submitted it for helium-4 analysis, and then made up the volume of gas that we'd taken from the cell with fresh deuterium containing 0.34 parts per million. So, in fact, we had diluted the gas. We expect now the second sample to have a lower value of helium-4 than the previous. What we in fact observed was that the helium-4 signature had increased rather than our expectation of it having decreased. This interested us. It suggested that the helium-4 was present and was being slowly made available to the gas for analysis. So we undertook an exercise with this cathode, making it an anode and a cathode in alternating cycles. So we went through some compositional variations and some thermal variations on the cathode, trying to force any near-surface helium out into the gas phase so we could analyze it. To make a long story short, after a considerable period of exercising this cathode, we made another helium-4 analysis, and if you do your mass balance and do your math correctly, which I didn't do, in fact, in my initial publication, but when you do your math correctly, you find that you achieve 104% plus or minus 10% of the expectation value. So quite clearly, the helium-4 is present. It's made available at more or less the level that you expect, but it isn't all presented into the gas phase for analysis. You have to work to dislodge the helium-4 from the lattice in order to put it in the gas, because we can only analyze, in this case, we can only analyze the helium-4 in the gas. So this is starting to make a little bit of sense, and we're starting to understand where the helium-4 is coming from, where it is presented. I promised helium-3 and tritium-2. Working very closely in conjunction with Professors Arata and Jean, who made for us, in fact, cathodes according to their normal method of production. Those that don't know the Arata-Jean double-structured cathode, I don't have a good picture of it, but basically it's a palladium bottle. It's a cylinder of palladium drilled out, into which is placed some small dimension palladium black, palladium powders of very small dimension, and then the top is sealed in such a way that electrolysis can be performed on the outside of this palladium bottle. Deuterium or hydrogen in the reference cells go through the walls of the bottle, enter into the void volume in the middle, the void volume containing palladium black. If there's any special properties associated with the palladium black, then we might hope for some heat production or helium production, as have been reported, in fact, on several occasions by Professors Arata and Zhang. So our experiment was really only intended to confirm work that had already been published and presented. The first aspect of that work was to confirm whether or not there was any excess heat production, and the only modification that we applied to the Arata-Zhang method was to use our water flow, mass flow calorimeters. If you look at the bottom, we had performed two identical experiments. We were simply presented with two cathodes, one of which we arbitrarily declared to be a blank and operated it in a light water electrolyte, the other of which we declared to be the active cell and operated it in a heavy water electrolyte. If you look at the results in the light water electrolyte, these cells are exercised at very high currents and very high powers. So if you're looking at the right-hand side, referencing a scale from 0 to 300 watts, which is large by our standards, exercising the cathode through various currents, and as the electrolyte changes composition and resistance, the voltages and powers therefore increase. This is the light water cell over a range of powers from 50 to 300 watts. The excess power that we observed in that cell is essentially zero, and there's a lot of scatter because the powers and the dynamics of the power are large, but for the light water cell, the excess power is essentially zero. If you look at the heavy water cell at the top, we have the same dynamic range of input power, 0 to 300 watts, but in this case, the excess power observed is clearly not zero and is clearly not the same as the light water cell. So in the simplest term, the claim made by Arata-Zhang, a heavy water cell produces more heat for the same range of input powers as does a light water cell. This is certainly our observation, so we're able to confirm that. This is not a large amount of power. If you plot these same results in terms of the excess power versus the input power, the light water result obviously is baseline. The heavy water result has this, and I've fancifully put a parabola through this, but it may have a shape something like this, diminishing to zero at a non-zero input power level, which is important, as many of you will remember, and also decreasing apparently at very high levels of input power. But we have something like 10 watts of excess power, and if you look at this thing in terms of a percentage, with some assigned uncertainties, the largest excess power that we observed in this experiment was called 10%, plus or minus 1.3%. But the signature is only in the range of sort of 7-8%. A signature sufficiently large for us to be confident that it's a real effect, but you're also doing a lot of work. You're putting 300 watts of input power in to only get 10 watts or so out. Something somewhat more interesting, the excess power is obviously interesting and important, but what does it mean? If you remember, this experiment, the double-structured cathode, has a hollow void inside. Inside the void is some palladium black. So we are able to make samples of various phases. We can sample the metal phase from the palladium black. We can sample the metal phase from the palladium walls. We can sample a gas phase, which I've partitioned into two components. The gas, because there's some oxygen inside, oxygen associated with the palladium oxide on the surface of the palladium black particles, some of the gas that's inside this void at the end of the experiment is in fact bound up in molecular water form, generically D2O. Some of it is simply D2 gas. So we can take samples. what we did in conjunction with Brian Oliver at Pacific Northwest Labs is make a machine which we were able to puncture this closed void volume double structure cathode and take gas samples for analysis. Also, after having taken the gas sample away for analysis, we can take samples of the metal phases and submit them for analysis. The initial helium results for the metal phase, you can look at both helium-4 and helium-3. This work was done by Brian Clark at McMaster University, probably the world's expert in helium-3 analysis. If you look at these numbers, you can see something quite interesting, in fact, that the palladium, let's just look at the palladium bulk. These are Clark units. Brian Clark, I call them Clark units. Brian Clark references his helium-4 measurements in terms of 10 to the 9th atoms per milligram. His helium-3 results in times 10 to the 3 atoms per milligram. But if we look at helium-4, we take a sample of the bulk metal submitted for analysis. In fact, we've taken many samples for analysis. We find something like 7.3 times 10 to the 12th atoms of helium-4 in the total volume of the cathode. We find 1.1 times 10 to the 11th helium-3 atoms in the total volume of the cathode. So the ratio of helium-4 to helium-3 in this case is 67. Those of you who know anything about helium-3 analysis know that the ambient background level ratio of helium-4 to helium-3 is 800,000. So instead of 800,000, we're observing 67. So the helium-3 signature in that case is enhanced by something like 12,000. We have 12,000 times the amount of helium-3 that one would expect if the helium-3 were naturally produced. For the palladium black, the situation is even more perturbed. In the palladium black, the helium-3 that we observe is 44,000 times the level that you would expect if the helium-3 were derived from natural sources. So this is clear evidence that the helium-3 is produced. Helium-3 is derived from something other than the process which gives rise to helium-3 in the atmosphere. It's not the end of the story, however. If you look at that a little bit more closely, you find several things. First of all, the persistence of helium-3 signature in the mass spectrometer suggested that the helium-3 that was there was not produced as helium-3, it came in as tritium. Helium-3 is not very sticky in the mass spectrometer, it will pump out relatively easily. What we did to poor Brian Clark, in fact, was put his mass spectrometer out of commission for something like 3 months. We submitted so much helium-3 to it that he wasn't able to use it for 3 months, for which I owe him dearly. In fact, the helium-3 sample that we gave him was more than 1,000 times larger than any sample that he had previously submitted to his mass spectrometer. If you look, or you can also profile in the radial direction the metal walls, and you find that there's a somewhat exponential gradient of composition of helium-3 in the metal wall. This is not consistent with the helium-3 being diffused. Helium-3 doesn't diffuse that far or that well in palladium. This is consistent only with the helium-3 being derived from the decay of tritium as the tritium was diffusing through the metal wall. So we can conclude that some or all of the helium-3 is due, in fact, to tritium decay. And if you look at the various phases that are available to us for analysis, remember I said before the palladium bulk metal phase, the palladium black metal phase, the gas phases, molecular D2 and molecular D2O, and could also look in the electrolyte. We take them all, do a mass balance, analyze as carefully as we can all of these phases for tritium. Find that all of them contain tritium, including the electrolyte, which for us is quite a shock because we have done more than 500 analyses, perhaps as many as 1,000 analyses of electrolytes for tritium, and in none of them have we ever observed tritium. This is the first time we observed tritium in our electrolytes. You can see that the tritium that's present, if you do a mass balance, you total it all up, there's something like 10 to the 15th atoms of tritium in this system. Most of it, 97.8% of it, is contained in the molecular phase, which is on the inside of the errata void volume. And to complete that story, the light water blank, we observed no anomalies in helium-3 and no tritium. And I just have the picture. Picture here of the gradient of composition of helium-3 as we observe it in the metal wall. Something as shown here. So my chairman is getting agitated. I anticipated he was getting agitated. Conclusions from this subset of our results, I suppose. There's a strong time correlation between heat and helium production via online high-resolution mass spectrometry. Quantitative correlation between heat and helium for production, according to a reaction which describes generically D plus D to helium-4 plus something like 24 MeV in the lattice. Once you dislodge all of the helium-4, which is lodged near surface in the lattice, these results obtained in 3 different metal seal cells, 3 different calorimetric methods, both electrochemical and gas loading experiments. The helium-4 analyses have now been performed in 4 different institutions, helium-3 analyses in 2 different institutions. Evidence for near-surface retention of helium-4 in the lattice, and clear evidence of tritium production and retention in, at, or near the surface of small-dimension palladium particles. Thank you.
We have 5 minutes for questions. Yes. First one.
It's a very interesting experiment. And I want to know, did you analyze the cathode metals in those cases? Palladium, carbon analysis, or other chance curve?
I think the question is, did we analyze the cathode materials?
Oh, yes.
The answer is yes. And there are a lot of cathodes. We're talking about results of 20-odd experiments here. In every case we've analyzed in some way, manner, or form the cathodes. What are you seeking? What information would you like?
What kind of nuclear products did you find on the cathode?
We haven't paid very much attention to seeking high mass isotope anomalies. And we've looked at various times, and in some of these experiments, and there might be something to say about it, but at the moment I'm not willing to discuss that.
I didn't get, you have to push something? I didn't get the, from the amount of, I didn't get the values of hydrogen and helium relative to each other, tritium and helium production. Did the tritium amount to any significant amount of the heat production? Production of tritium was not a significant, can you give a number to that? Is it less than 1% or less than 10%?
Seeking a correlation between either the production of tritium or the production of helium-3 and the appearance of heat in the errata experiment, less than 0.01%. The amount of heat observed in that experiment was very considerable. No significant fraction of it was associated with the observed helium-3 or tritium.
Okay. And I think you should mention that Arata was the one who also first found helium-3.
I'm sorry, that is a very legitimate point. We have neither developed this method ourselves in terms of its calorimetry, nor are we the first to observe helium-3 as has been observed by Arata and John.
Your results seem to be very impressive. I have
Seem to be.
very impressive. Our colleague looks impressive. Oh, very impressive. But could you summarize 3 ratios? The amount of helium-4 against helium-3, and then against tritium. What is the ratio of those 3?
The different phases have different ratios. And the easy one to answer is tritium to helium-3. Is all the helium-3 that we observe derived from decay of tritium? I don't know. Our analyses are not accurate enough at this time to know whether helium-3 was born independent of a tritium decay channel. I don't know the answer. If you do a sort of generic add up and figure out what the total helium-3 to total helium-4 signal is, the ratio is about 1/3. But most of the helium-4 that we observe is probably derived from the ambient. The amount of helium-4 that we see is not large. So, you know, the expectation value, helium-3 to helium-4 is 1 part in 800,000. We see 1 part in 3.
Is that consistent with the Arthur's observation?
Yes? Yes.
Mike, could you just clarify one point? The error bars, are they 1 sigma on your diagrams, or what are they?
Yes. In general, the error bars are just 1 sigma analytical errors. The helium-3 analyses, the errors, absolute errors are small, less than 1%. And Brian is able to measure 1,000 tritium atoms. Sorry, 1,000 helium-3 atoms, and we're seeing 10 to the 12th, so the analytical errors in helium-3 are very small.
Hello. But my question is rather, it was very difficult physics. You talked of coherent phonon modes. So I would suggest that some experiments should be done in future. So what are the specific phonon modes which are coherently involved in the process? Maybe the density of states of specific phonon modes, their measurement may be required.
Is this question rhetorical? I would ask you this question.
But we have plans of experiment.
Okay, we have just the last fast question.
Yeah, a very simple question. Did you, in the errata experiment, there was a considerable amount of hydrogen in the, I think they used LiOH for the salt. Did you have a lot of hydrogen in your system too?
We attempted to reproduce the errata-Zhang method as closely as we could. So we made our electrolytes up in the same way.
Exactly the same way.
Which is to use 10th molar LiOH.
So there was a lot of protium around.
It isn't a lot, actually. When you do your sums, it's
sure,
sub 1%. But as you know, hydrogen preferentially absorbs into palladium. So,
sure.
And to answer the question you're really asking, was there a lot of hydrogen inside the void volume? The answer is yes.
Okay, thank you, Michael, for your interesting presentation. Next speaker is Professor Saji.
It was well presented, the work is well done.
Presentation was even better than the ACS. Had all that new stuff on it. I helium-3 and finally helium-4 day. Really great.
Okay. First of all, thank to Professor Scaramuzzi to to take the opportunity to give a talk here. And I think this place is very nice, and we have good, beautiful weather, and I enjoyed very much staying in this little town of Italy, and I also enjoyed very much this conference. And today, I just want to talk about the recent our research project, which is underway in my institute, Laboratory of Nuclear Study, Nuclear Science at Tohoku University. And our first aim to see this phenomena, I would say the nuclear phenomena, which might be influenced or affected very much by the environment. For example, the electrons and the lattice and so on. The most famous effect is, of course, the Mess-Bauer effect, which is just a recoilless gamma ray transition. And those recoil energies are shared, the whole lattice themselves. So the gamma ray, the transition energy is completed converted to the gamma ray energy without any loss of the energy. And also, we know that many effects on the beta ray lifetime measurement, so-called chemical effect. Of course, these are very small effects, though, but sometimes the lifetime was changed, something around less than %. And also, our Nuclear Physics Society is also interested to see the very low energy nuclear reactions, which might be related to the astrophysics problem, because in stellar conditions, we need a real reaction rate in low energy nuclear reactions. So there we also find a screening effect, which is mainly caused the difference of the wave function of the electrons around the nuclei. So if the nuclear fusion in solids at the room temperature occurs, we really need two things. Coulomb barrier should be lowered tremendously. And also, as the results of the previous speaker, Mike Matkubo, he told us that the branching ratio of the DD reaction mainly goes to the alpha particle emission. So another question is, branching ratios are completely different from our present knowledge. So these are the two main questions we want to ask. And as an experimentalist, I want to know I want to get real experimental result. Therefore, we have been studying, does the environment of a nucleus strongly affect nuclear reactions? And in these several years, we did low energy nuclear reaction in solid. For example, DD reactions, let's say something around the keV order, incident energy is keV order. And in the last conference of the ICCF conference, we just showed the strong evidence of the enhancement of reaction rate just for palladium and palladium oxide. And after that, we continued what kind of mechanism and if there are any other materials which can enhance this reaction rate. And also, very recently, we started to study the lithium plus D reactions again in palladium. And we are planning now this kind of reaction for the other materials. Just go to the result. I just show this figure. This is the how the screening. This is to explain how the screening occurs. For example, I just take the very simple case. Our target nucleus is of course surrounded by electrons. For example, this is the bound electron mixed atom. Therefore, if the projectile nucleus coming outside the atom, there's no Coulomb repulsive force. And but if you enter the so-called the electron cloud, the atom no projectile suddenly sees the bare nucleus. So there is a strong repulsive force. If the incident energy is much higher, then usually it doesn't produce any effect. That the reaction cross section is just depend itself. But if you lower the incident energy, the effect of this electron is very much. For example, we call this is the Coulomb barrier. So inside the nuclear radius, the interaction is very strong, so-called the nuclear forces. Therefore, up to here, you can make a nuclear reaction. Otherwise, the projectiles are repelled by the strong Coulomb barrier. But if the electron is outside the nucleus, the barrier height is of course reduced. And so it can be approximated simply just putting the screening energy, US. So therefore the reaction cross-section is enhanced because of the your projectile get another energy, US, screening energy from the screening. So this is so-called screening effect. And usually the low energy fusion reactions can be described by this formula. And this part just show the Coulomb penetrability. And if you have a screening effect and you have a screening energy, which enhances the cross-section very much, and you can estimate cross-section just to use the incident energy plus screening energy. And so far, we know for the gas phase, for example, D plus D reaction with a gas target, there's an experimental value, deduced value for the screening energy, something around 25 plus or minus 5 electron volt. And this is almost the same value as a simple estimation, which gives us just 27 electron volt. And also, if your deuterium is inside the metal, it is said that the screening energy is bigger, something around 50 to 70 electron volt. And also, for the lithium plus D system, there is measured values. Screening energy is something around 0.38 keV in this case, which is reduced from the lithium fluoride target. And a simple estimation gives us this energy is something like 0.24 keV. So these values are almost explained by just a simple screening by electrons. Just to tell how difficult to measure this kind of screen energy. This is for the D plus D case. So if you have a no screening, your cross section is going down very quickly. For example, you have a 10 keV cross section, something around 10 to the minus 6 farm, and if we go down, let's say 1 keV, the difference is more than 12 orders of magnitudes. And but if you have a very large screen potential, then this ratio is reduced to the small values. For example, for 1 keV, maybe the 6 or 8 order of magnitude. To do that, to measure it, we constructed the low energy high intensity beam generator at our laboratory. And this machine is very small, just you can put just on this desk. And the point is we use we make our D plus beam from a duoplasmatron ion source. And we separate the molecular beam and atomic beam just using this bending magnet. Here we have a deceleration electrode because we need a very high current to do this kind of experiment. And therefore we need external voltage to extract the beam, something around 25 keV. Therefore, the beam energy is 25 keV here. Then we decelerate the atoms, the ions, by using this electrode. And here you have a very low energy deuterium D plus or D plus beam. And the point is that even you ionize the gas, some of the gas can be neutralized during the transportation. So therefore, that if you have a D atom around here, the D atom is not decelerated by this electron and goes to the target directly. So we put the neutral beam filter magnet over here, just separate the very high energy neutral atomic beams. Then all the deuterium beam is D plus, very low energy D plus beam. We have, let's see, in this small accelerator or ion source, we got a beam from 1 keV to 100 keV, and the beam spot at the target position is something around 3 mm5, and the beam current is 5 microamperes at around due to energy of 6 keV, and at 2 keV we got 200 to 400 microamps. And target, the detector we employ is just a silicon counter telescope, which consists of 50 micrometer delta E silicon detector and let's say 150 or more than that, 500 micrometer E detector, and we cool down the target to contain to keep the deuteron inside the metal. Otherwise, if you do the measurement without the cooling, the deuteron, for example, in palladium, get away immediately. So we cannot measure we cannot get the real low energy data. So the target is cooled down by using the liquid nitrogen. And target used we did a various target: titanium, gold, iron, palladium, palladium black, PDO, PD gold structure, which the Lipson brought to us. And for this palladium oxide case, the surface of PDO ore was bombarded by the deuterium itself. And after that, we did a palladium lithium. The ratio, atomic ratio of the lithium is something 0.07. This is a typical two-dimensional spectra for the proton. I mean, the D plus D make up proton plus tritium, and this is the 3 MeV proton emitted from that reaction in palladium oxide. In this case, the incident energy is 4 keV, and you can clearly see this is the correlation, energy correlation for the delta E detector and delta E detector to the E detector. You can see the correlation. So and all the electronic noises are just doesn't have any correlation. So therefore, the identification is very clear. And if you sum up the energy of the E detector and the delta E detector, you can see just one peak. Because we put the absorber just in front of the detector system, the tritium and the helium-3 it cannot punch through that absorber. Therefore, only one peak, just around 3 MeV. And this is the proton yield for proton spectra for 6.5 keV, 4.3 keV, and 2.6 keV. Of course, the yield is getting lower and lower. Usually, we need maybe something around 1 week to get this kind of spectra. And we studied how the deuterons behave in metal during our bombardment, because you see the atomic deuteron coming and implanted in the metal. It stops around the range, of this. It is very close to the surface. Then after that, the deuteron is diffuses anywhere, in this way or in this way. And another deuteron can make a reaction just close to the surface, because if you go into deeper to the from the surface, then you lose the energy. Therefore, the reaction rate is going down. So what I'm showing here is the proton yield versus time. I would say time. If you are putting the deuteron continuously, I mean almost a constant value of deuterons, then it is just going down. So this shows the concentration of our target deuterons. What I want to say here is, after the sum of the bombardment, this is the case for the palladium metal, and this yield is just saturated. That means the saturation of a deuteron concentration inside the metal. And another one I want to say here is this value does not depend on the beam current, and even if you started the old stuff which already implanted deuterium inside the metal, this amount is almost same, similar value we got. But this value depends on the host material very much, and also depends on temperature. Okay. I spoke so slowly.
You must place the importance.
All right. So I have various things which I just give you confidence of our result, but I all skip. Sorry, and you can of course ask to me after my talk. And then what I want to show you is one thing over here. Is how I analyze the data. Because this method is using so-called thick target method. Therefore, as I told you, the incident neutron is slowing down, losing his energy. Therefore, what we observe is all the integration of the yield for the different energies, like this. And what we need is the number of target neutrons versus depth. And we just assume this is the uniform distribution. And also we need this kind of cross-section. And what we did is just compare to the bare cross-section. So we just put the bare cross-section, which is the parameterization of Bosch and Hale. And also we need a stopping cross-section, stopping power for the incident neutrons. And we use this Anderson-Ziegler's table for that. Okay, so this is the result for the DD reaction in palladium oxide, which I already showed you this result at the last conference. But after that, we have another measurement. So the PD of first and the PD of second. And those values fall almost same value very nicely. So the reproducibility, I just checked the reproducibility. And from here, I got the value of the screening energy for the palladium oxide. It's a 608 electron volt. And for the palladium black and the iron, the reaction cross-section is somewhat enhanced. Of course, again, this is very much enhanced, but somewhat smaller than for the case of palladium oxide. For example, in this case, for the palladium, the screening energy is something like 310 electron volt. And for the iron, we would say it's something around 200 electron volt. And there is a metal, some of the metals cannot show any enhancement. A little bit enhancement, but not so big. For example, the gold and the titanium, the screening energy is something like 60 or 70 electron volt. If the screening energy is some 600 electron volt, our cross-section, our estimate cross-section is drawn by a red line. And you see for the thermal energy, room temperature energy, the cross-section is something like 10 to minus 16 bar. And it goes, the reaction rate is 3 times 10 to the 7 per second per cubic centimeter. If we can apply the thermonuclear reaction rate formulation for this case. All right. We summarize the case palladium oxide, palladium, and iron. In this case, we will say these values cannot be due to the electron screening alone. Therefore, we need a new mechanism to explain another mechanism to expand this enhanced cross-section. Because, as I told you, that usually the screen energy from the electrons, something like, it is something like 50 to 70 electron volt. And I just showed the one graph for that. There might be the correlation between the screening energy and neutron density for these various metals. It's just a curious behavior, because if the density in the neutron is lower, then you got that very enhanced screening energy. And we are thinking that it might be related to the fluidity of a neutron in the metal, because if you change the temperature, this is the density versus temperature, and if you change the temperature, the density changes very much for the palladium oxide palladium, and for the titanium or the gold, it does not change so much. So therefore, this reduction, I mean the density reduction, correlated to the fluidity. Therefore, the large fluidity material might make a big enhancement. And I think I have another one slide, two or three slides. Okay, so this is the another reaction system. Lithium plus V go to alpha plus alpha helium 4 in palladium. So this is just the excitation energy, and the incident energy is 30 to 75 kV. We normalize the reaction rate here again, and what we got is very enhanced reaction cross section. The screening, in this case, screening potential energy is 1.55 kV, and for the lithium 7 plus V, we got almost same value, 1.76 kV. And you see, for the lithium fluoride case, the screen energy is 0.38 kV plus minus 0.25, and the adiabatic estimation is 0.24. So this again cannot be explained by the electron screening alone. Okay, so finally I just summarize my talk. So the DD reactions can be enhanced extraordinarily when the reaction occurs in a particular host material, such as palladium oxide and palladium. I just show the rough number of the screening potential. And also in palladium metal, the lithium plus D reactions are enhanced very much. And again, the screening energy is something like factor of 5 larger than the electron value. These findings cannot be explained by electron screening only, and we really need to explain new mechanism in solid. And for the cold fusion research, I said there are two questions. So the number one, can Coulomb barrier be lowered in solid, or can the reaction rate be enhanced in solid? Our conclusion, I can say yes, there is real enhancement in solid. And the number two, can branching ratios of this reaction be completely changed in solid? We have not answered yet by now. So we still to seek for example, alpha emission in D plus D at several keV. Thank you.
calculating the screening problem, particularly. We have been calculating the screening problem using your data. And the idea is that our approach is that the electron screening, and we find that if there is a strong electron-phonon interaction, and also a strong exchange interaction, exchange correlation to d electrons, and then the electrons pair with not only single electron, but electron pair to be more stable, electrons to be localized. And your data is very supportive of this idea that there will be a strong electron-phonon interaction in palladium oxide, so it will be more a stronger screening effect. So I think that what your result is very beautiful from this point of view. It shows the role of interaction with phonons, and for the electron-phonon interaction, the electrons can be acquired from mass, they can get localized, and pairwise localized around the neutrons.
Can you get the, such kind of big screening potential energy then? Order of several hundred electron volt? Okay.
I have a question. Your experiment is low energy nuclear reactions inside above bombarding energy 1 kV. And for the deuteron with 1 kV, the speed is similar to the thermal velocity of electron. That means the 1 kV is the Born-Oppenheimer approximation limits usually used in the solid physics. So I guess the extrapolation of your experimental data to the thermal energy is nonsense. How do you think about this point?
Well, I just want to measure the real, we want to go down more and more, and we will see. That's I want. But right now, what I have is just the value of this energy. So I just extrapolate it. That's it.
To solid and surface, you mentioned this palladium black, you had a strong increase. So this is for surface mechanisms, not so much for.
Well, you said palladium black? Yes. Yeah, we bombarded palladium black once, and the value is similar to the palladium. And the PDO case, it is very much enhanced.
Back to several previous questions, what would the deuterium loading ratio be in your target to be relevant to what we are interested in? It would seem you need to devise an experiment where you get a very high loading ratio.
That's right.
You have coherent effects involved.
For this experiment, we cannot put the deuterium, especially in palladium, because it is diffuses, and our experiment in vacuum, so always the palladium and the deuterium in vacuum is get out from the surface. So the loading ratio, I would say, in this very surface region is something like percent order. And just if you go the inside, this ratio goes very high during the bombardment. Maybe go to the 0.5 or something like that. But in this surface region, it is very small. That is true.
Let's see, to underscore the physical significance of what your measurements seem to imply, in the case of deuteron-deuteron collision for gas phase, the screening energy of about 25 electron volts corresponds roughly to 1 Bohr radius or the screening distance, which is what you expect for the molecular problem. Correspondingly, the screening distance associated with your measurements of 10 times that energy, that corresponds to 10 to the 4 radius or even less. there's that has to correspond to something happening physically on that kind of scale, and that's proving to be extraordinarily difficult to understand theoretically. Is there any chance whatsoever that you let us steer us off the hook by finding some experimental artifact for us?
The things is one of the things we have to be very careful is the changing of the number of the target neutron, just the surface region. As I told to him, because of I said that there's number of the neutron, target neutron is almost stable, but actually it is fluctuated. So we have to correct for the number of neutrons. Normalized. Just we measure the neutron before the bombardment and just after the bombardment. This is a very short run, just maybe 1 or 2 hours, and measuring the things again and again. And also, I guess you have another suggestion to do that. Yeah. Okay.
I was curious. When George Miley's comment about the loading made me think of something. Russ George has had tremendous success using silver in some of his cavitation experiments. And the electronic structure of silver is very similar to fully loaded palladium deuterite. Have you considered using silver?
We didn't measure the neutron silver yet, but and why we cannot put the density to, I cannot put the high density. I cannot realize high density.
Yeah, you don't have high density.
That's right. That's right. Needed. Well, I just right.
Great. Again about loading. My question is why you don't before load with the gas and that's cool at the liquid hydrogen temperature and that's bombarding. So two-step process. Why don't you adopt this technique in order to increase the starting loading of deuterium and palladium? Because at the liquid hydrogen temperature, the loading keeps stable at a very, very large value. And that's apply bubble. Okay, about maybe a possible techniques in order to increase loading of your target is to load by gas loading from temperature up to liquid nitrogen
before
yes, and that's
we did that, but just put the vacuum, then that does go out quickly.
You were talking about the possibility of the branching ratio changing. Now, the branching ratio for helium-4 with respect to other particles is down a factor of 10 to the 7th. Now, only 10 to the 2 of that becomes because it's a weak interaction, not a strong interaction. And the other 10 to the 5th becomes of spin considerations. If you have such strong screening effects, would this affect these spin considerations?
Sorry,
when you calculate what is the branching ratio of helium-4 production to helium-3 or tritons and things like that, you get an answer of 10 to the 7th. And experimentally this is observed. But if you have a very strong screening effect, like the 600 electron volts you say, would this affect this branching ratio calculation? Because the branching ratio of 10 to the minus 7 is in two parts. One is weak interaction to strong, and the other is spin effects.
Okay, anyway, the gamma channel is just an electromagnetic channel, not a weak channel.
But the spin
but anyway. Okay, so my point is two things. One thing is we can really realize the situation in which the Coulomb potential is really low than the bare reaction case. And also there might be another transition, not a usual electromagnetic transition, but if the compound nucleus can interact with the other things and then goes to the ground state directly without electromagnetic transition. That might be happening. That's my question.
Thank you.
Yes.
Next report will be Professor Stokes.
It took all that time.
Over the last 11 years, I have studied about 175 different samples.
Yeah.
Over the last 11 years, I studied about 175 samples of palladium, only a few of which made excess energy. Most of that work was an effort to understand the variables which affect excess energy production. Many of you here also have contributed to that understanding. I would like to suggest at this point that once palladium has been manufactured, no variables remain, a change of which will produce excess power in a reproducible, consistent manner. In other words, heredity is more important than experience, nature over nurture. To solve this problem, it's necessary, therefore, to manufacture our own palladium. Now, one way of doing that is by electroplating. That also has the advantage that it makes thin films, which in the past have shown excess heat production. So I undertook to explore electroplating palladium, and have come to the conclusion, after much effort, that it is just as difficult to reproduce palladium by that technique as it is by making a bulk sample. However, during that effort, I experienced a very unexpected event. One of my platinum samples that I was using as a blank for calibrating the calorimeter suddenly produced excess energy. And rather than tell you about a lot of experiments that didn't work, I would like to tell you about that experiment which did work, because it has a big impact on our understanding of the Ponce-Fleischmann effect. I've noted here a website. This is, in fact, the first successful cold fusion experiment which is available on the web. All of the primary data, all of the raw data is available. Anybody can come in and do whatever they want to with it and decide for themselves whether it's real or not. And a number of people, some very determined skeptics, have done this, and I will tell you about some of their comments as I go along. Well, before I can expect you to believe that platinum can make excess energy, I've got to convince you that my calorimetry is good enough to see it. The calorimeter that I'm using is a dual type. It measures the excess energy both by the flow technique and also by the isoparabolic technique. It consists of a glass jacketed cell which is contained in a glass door with an insulated lid. The temperature of the water going into this is measured, and the temperature of the water going out is measured. The flow rate of the water is also measured, but it's very constant. Within the electrolyte, there are two thermistors, one at the top of the electrolyte, one at the bottom, and another that's not shown there that's right next to the cathode. These two thermistors are used to measure the average internal temperature, and of course the jacket temperature we know. The inside is also a recombiner, a heater for calibration, and a Lugum capillary that communicates to a reference electrode on the outside for measuring open circuit voltages and over voltages. The cell is stirred by a digitally controlled stirring motor. And then this whole device is contained in an environment which is held to a constant temperature of a few hundredths of a degree. Here's a picture showing the stirrer, the door, The sample is down inside. This is the box that it's contained in. All of the circuitry, reference electrodes, reference resistors, and so forth are also in this constant temperature environment. This is a picture looking down into the door. You can see the glass. This is a little hypodermic needle or hypodermic syringe to pull the solution in contact with the reference electrode, and then the various connectors. Well, this can be calibrated. This is the calibration for the flow type calorimeter. It can be calibrated two different ways, both by the electrolytic technique and by the joule heater. The two give essentially the same answer. They're very close, indicating that it doesn't matter where within the cell the heat's being produced. It's capable of capturing about 98% of all the heat that's generated inside of the electrolyte. The isoparabolic calorimeter can also be calibrated two different ways. This is the calibration based upon the electrolytic technique, and this is the calibration based upon the heater. Now, you'll notice, first of all, that this is nonlinear, which is typical, but these two don't agree, and that is also typical. And I would suggest that it's a very dangerous policy to use a heater to calibrate an isoparabolic calorimeter. I've done quite a bit of study of that, and that would take another hour of my lecture to explain, but this is typical. You cannot use a heater, really, to calibrate an isoparabolic calorimeter because the heater and the electrolytic action produce different stirring actions and different gradients within the electrolyte. Well, the sample that I want to describe was intended to be used as a calibration sample. It's a piece of palladium, or a piece of platinum rather, that I had used in the past, and because of a certain amount of laziness on my part, I had failed to clean it. Thus, you're hearing about it. Otherwise, I would have nothing to say. But this is what happened when I put it in with the intention of getting its calibration. This is a excess power against applied current. And as the current was increased, it showed no excess power, just as I expected, but all of a sudden, excess power started to be produced. And then as the current was increased, and then the current was allowed to come back down in steps, and it now went down on a line different than when it went up. So it had essentially been activated. You'll notice that the isoparabolic calorimeter, which is an independent measurement of heat, produced the same effect. Nothing here, and then it started to rise. So that got my attention. And the sample was then taken out, and a piece of pure, clean platinum was put in, the calibration from which you just saw. After that calibration was run, the sample, the active sample, was put back into the calorimeter, and you can see the time history of application of various currents. Now, this is starting to run here at 0 time. This is excess power. The first thing I did was apply current in stages, and this is done by increasing the current, allowing the calorimeter to come to equilibrium, which is about an hour, and then 5 points are taken, and then the current is stepped again. And it stepped up to 3 amps and then stepped back down. So you can see that this power grew in as the current grew in, and then it went back down. We'll see this plotted in a different way shortly, and we'll gain some insights from that. After this sweep was made, I went to a 0.5 amp, and it went to here, the current, the excess power, 1 amp, went to here, it was held very nicely. I went to 1.5 amps, it held for a little while, and then it started to decay away. And it went to 0. Now here another sweep was run, just exactly like this one, and you see you have essentially nothing happening. Put a 0.5 amp on it, nothing, flat. The thing had died. And at this point, the current was turned off. Now when the current was turned back on after about 15 minutes,
half an amp was put on, and you notice it had come back to life again. It had been resurrected by this short vacation. And I'm now getting excess heat based upon a half an amp. I do another sweep. Well, there it is again. Put a half an amp, 0.75, 1, go up to 1.5 amps again. It dies again. Again, I turn the current off. Again, a half an amp produces a little bit. I go down to 1/10 of an amp, essentially zero. There's a little slight offset. Back up to a half an amp. I do a sweep, another sweep, and I'm getting excess heat again. Well, that's hard to explain by error or by any prosaic explanation. But I, at that point, put the information on the internet. And of course, there were very creative people out there that came up with all kinds of ideas. Let me show you a summary of these current sweeps. There were two platinum calibrations, one at the beginning and one at this point in the time, and those agreed. The current sweeps that showed excess energy agree with one another at the various times. They were taken at various times, but they all agree with one another, and they lie on a line which extrapolates down to zero power at zero current, which is quite different than the way palladium behaves, as I will show you. Well, anyway, so the people on the internet came back and suggested various explanations as to what was going on, and I attempted to answer some of those explanations. The sample was put back into the calorimeter. It showed excess power again, a half an amp. Then I went up to a higher current, and it died fairly more quickly at the higher current. And in order to turn it back on, deloading didn't work this time. In order to turn it back on, I had to take it out and boil it in water. So obviously there's something going on the surface that is interfering, and you can remove it by just allowing it to dissolve off if it's not too thick. But if it builds up too thickly because of the current being too high, you have to take it off by more robust means. After having boiled it, you can see I was getting excess heat, and then I did this study. There's 3 sweeps done in a row. They were done taking a different number of data points. Now, I should go back and explain what one of the explanations was. The assertion was that when the current was being applied, an AC voltage and current was being introduced on the leads, and my data acquisition were missing the spikes that were being generated. And therefore, since I was missing input power, but measuring output power, it would look like excess energy was being produced. Now, there were a number of ways to get at that, and I chose to use the following. Normally, I take 15,000 data points and average them for each of these points here. And so I chose to take fewer. I took 15,000, 1,500, and a smaller number. The theory there being that if I were missing these spikes with 15,000 data points, I would be missing even more of them with 1,500 data points. And so I should not see agreement when I did these scans. And here is the result. This was, in this particular case, I went from 10,000 to 1,000 to 100, and you see they all agree. It would appear that the spike theory does not hold water. In addition, I also did a calibration using the internal heater, and it's right on 0. So there was no shift in the sensitivity of the calorimeter. Then the assertion was that I was calculating the power incorrectly. That really you have to, I was measuring the average current and measuring the average voltage and then multiplying those averages. They said, no, you can't do that. You have to take the voltage times the current and then average that to get the power. So I made those calculations, and you can see the difference between the average current times voltage minus the average of average voltage times average current. The difference is plotted here against applied power in watts, and you see there's essentially no difference. That is not an explanation. There's more scatter, of course, as you go to fewer data points, but that's to be expected, but it's scattering around zero. Anyway, so I was pretty much able to shoot down all of the creative explanations by the skeptics, as far as I can tell, and perhaps some of you will come up with some ones that have not been suggested, and I'll be happy to address those. One of the things that we need to understand is that the relationship between current density and excess power in the palladium system has a different behavior than is apparent in the platinum system. And the difference, of course, is that there's a critical onset value before anything is seen in the palladium system, and then it shows this straight line relationship. Why doesn't platinum behave the same way? Well, I would suggest the reason is that in the palladium system, there is a certain loss of deuterium from the surface that has to be overcome, because the deuterium can diffuse into and through the substrate, through the palladium. But in the platinum system, that's not possible, because platinum does not dissolve deuterium, and the diffusion rate is very low. So there is no loss rate that has to be offset by additional availability of ions to the surface. So that difference is perfectly understandable, and it's basically what you'd expect. Well, get to the conclusions here. Up to 800 milliwatts of power, that was 333 kilojoules of total energy that was produced by this particular sample. The behavior showed completely reproducible patterns. There's a linear relationship between applied current and excess power. And it suggests that other metals which are found to produce excess energy may involve this surface layer. Now, I just wanted to make a few personal comments. Many of you have produced results that have forced conventional science to have an open mind, to a large extent without success. Now I'm asking those of you who have committed your interest and efforts to understanding palladium to also have an open mind. That perhaps you're barking up the wrong tree. That it isn't really the metal, it's something that's being deposited on the metal. And palladium is not the best substrate. And indeed, people ask me, well, what am I to use to calibrate my cells? You know, what's dead? Well, clean platinum is dead. No doubt about that. But obviously it can come alive. And with some humor and a certain amount of irony, I suggest that you use palladium. Thank you very much.